All right. If it helps to, work at your lab station and remain at your lab station, more than fine. If you want to go to your lab station to do like your work and then come back together to talk about it. If you want to try just standing, if that helps you engage, so please, today could be like a trying different things. Okay, can we imagine solution formation on the particle level? So when we are talking about breaking solute attraction, what are all the different types of solute attraction? If I could just go through that. Well, if it is an ionic soluble, and so solubility rules, do we know what are always soluble? And so just to remind us, remember, potassium compounds, sodium compounds, nitrate compounds, what else? It's okay. Chapter 4, we haven't really talked about this. Are there other always soluble? Two more. The only positive polyatomic ion. Yeah. So no matter what they're paired with, if it has ammonium in your compound, of course, the rest will be non-metal or metals. So we know if they begin, even this, we treat it as a metal cation, that they're going to be soluble. There's one more anion that makes it always. Begins with A. Ends with E. You got it. Formula. Usually you're given it. So go. Say again. Excellent. Excellent. So we have acetate ammonium, 2 alkali. Oh, A's. Huh. 2 alkali metals, ammonium, acetate, and nitrate. Okay. If we have, for example, potassium nitrate, well, we know when that's put into water, it will D-word, dissociate. And so for it to dissociate, what is the particle attraction that has to be overcome? Go ahead, Reagan. Perfect. In general, how strong is that? Holy! We would rely on Coulomb's law to help us interpret that. Very, very strong. All right, that's if it's ionic and soluble. One more question. When we create a solution, is that a chemical reaction? No, it is a physical change. We are making a mixture. Mixtures are physically combined and can be physically separated. Okay, so if it's soluble and ionic, we're breaking electrostatic attraction. If it is polar covalent, we are breaking dipole-dipole, definitely Lund dispersion, and only Lund dispersion if it's nonpolar. We could be breaking hydrogen bonding. So you can't forget all those wonderful things that we talked about. Okay, and then usually our solvent is water. And so ultimately, of course, we're breaking hydrogen bonds. Okay, so the question is what we have to invest. So to break attraction, it is always endothermic. We know that. And when particle attraction forms, that's going to release energy. But the question is, do we have to invest more than is released? Or do we get out more than we have to invest? Okay, so just to address, and then if we need to discuss more, let me know. So for what's in green, it should be endothermic, then exothermic. And then B, it would be Lund dispersion because they're both non-polar. And then, because they're both going to have a Lund dispersion, they're both non-polar, so they'll have just Lund dispersion with each other. Yes? Any questions here? Okay, so continuing onward. So, excellent, Reagan, that you already gave us the answer to C, and that is electrostatic attraction. And that is, again, Coulomb's law. And so opposite charges attracting, this would be +1 and -1, and then the distance between the ion centers. In the solvent, of course, if it's water, which it will be, then hydrogen bonding will be the strongest. We could say Lund dispersion, dipole-dipole, and hydrogen bonding if we need to list all three. And then what can form between them? Go. Okay. Before we continue onward, the lab things that we did prior to, that lab with chapter 10, where you had the acetone you added to the blue glitter, and then you had test tubes for Christmas. So I know, might not remember crystal clear, not expecting us to. Okay. So sorry. It's taking me a moment. All right. So you had yellow food coloring dissolved in water. You had blue dye dissolved in acetone. You mixed them, and depending upon how much dye you were able to dissolve into the acetone, you may have gotten slightly green or a little more green, or you just kind of remain more blue than bluish green or greenish blue. But then you added salt, and you shook it, you shook it, you shook it, and then you let it sit. Now, when I was trying this out for us, I got blue dye, blue glitter from different manufacturers, because not all blue glitter is the same blue dye, believe it or not. And so one of the blue glitters, like, had some purplish, and so that's all confusing. It gave us some pink. So I made sure we didn't use that. We just got the separation again of the yellow and the blue. And then you were asked to explain why. You guys did a very, very good job. Okay, I'll only share means if they're good. I'm sure you've seen this a gazillion times. Now, shame on that young man. Shame on that young man. So no way, shape, or form am I saying that's okay. Gentlemen, if you are with your sweetie. Now, if you shouldn't be with that sweetie, why are you with the sweetie? But obviously, he's with her. Don't look. But does this represent what's going on? So the water was hanging out with the acetone, all right. Hydrogen bonding. Oh! But then the water had the chance, to ion dipole with the sodium and the chloride ions. Why didn't the acetone? And so many of you just nailed it to say the water molecule, it can create a stronger ion dipole. How do we know that? Well, we could tell that we got the separation the yellow was originally with the water. The blue was with the acetone. So why did they separate? And we see the sodium chloride is here. So it must have dissolved here, creating a more dense solution. So obviously the water went with the sodium chloride, not the acetone, because it's all about which will release more energy. Which will release more energy. So going back, when we had to make our solutions, and I had us either create a sodium chloride solution, false, a calcium chloride, or a sodium hydroxide from solid. Yeah? And did any of us, it felt warm when it was being dissolved? And then if you made a dilution of sulfuric acid, that got warm. Physical changes. Why? You were just making solutions. Well, usually the energetics are minimal, so we don't really observe it on the grand scale, but you did in that lab. So what is being pictured here is showing us, okay, these are like the steps, but this is trying to show us energetically. So to share the answers, below this graphic, the first should be, now when you're filling in the blanks, there of course could be like different choices that you come up with, but I would say the first fill in the blank is endothermic, and then positive, and then invested, absorbed, required. Anyone come up with a different term? Is greater than the energy that is, sorry about that, delta. I forgot, so erase that. That is released, or any other better terms that you guys came up with? Given off. Perfect, 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 perfect. And not one is better than the other. Okay, so endo, how would that feel? Class, how would this solution feel as it's being made? Cold. Do you know when you dissolve sodium chloride, it's an endothermic heat of solution, but usually it's of such small amounts that we really don't recognize the change in temperature, but it's endothermic heat of solution. Okay, so what would have to be true for it to be exothermic? And remember, when delta H, change in enthalpy, is negative, it's releasing energy. Well, the energy that we have to insert would have to be less than what's released. We're talking about the overall process. So we understand there's 3 steps. Well, what would make us negative overall? Breaking attraction is always positive. Now, what do we call step 1 and step 2? And really step 3. So in our humanness, we say, well, the solute attraction has to be broken. But those steps all happen simultaneously. So it's not that happens first. We just, in our humanness, say that usually happens first, or has to occur before the solute and solvent can attract. So just realize that. Okay, questions? Okie dokie. So could I have us focus on this graph, which is solubility versus temperature? Solubility versus temperature. What is solubility? What is solubility? And, you know, we have sodium chloride here, something we're familiar with. Glucose, familiar with. And if we look at, as we increase temperature, in general, what's happening to the solubility? Okay. The units of solubility are gram per 100 milliliters of water. Alan, what does it mean if something is soluble? Perfect. So those 3 steps are going to be accomplished. But every solute has a different amount of solute that can be dissolved per the amount of solvent at a given temperature. To this day, my brother thinks that someday he's going to be able to dissolve the whole container of sugar, of sucrose that you purchase in pounds, in the 2-quart container to make Kool-Aid. He's just, because my brother, just a year and a half younger than me, to this day, will just pour in like half the bag, add the water, the Kool-Aid, and he gets that. I think he really likes that sugar slurry thing. I'm like, what are you doing? That is always going to be there. I think he likes it. So all power to you if you do. We know there's no way. There's a limit to how much can be dissolved. That has a lot to do with the chemistry of the substance and the particle attraction. So for example, glucose, no, not sucrose, but glucose at room temp, we can only dissolve what, about 110 grams in every 100 milliliters of water. If you try to get more of that, it's just going to lay on the bottom. To deliver the solubility, that gives you a saturated solution. If at 25 Celsius with 100 milliliters of water, I only add 20 grams of glucose, I can add more. It is unsaturated. Now, if my brother boiled water and at 100 degrees added glucose, well, look, who knows? He'd get a lot more to dissolve. Who knows how far that goes up? Then if he cooled it down, and if that dissolved glucose remained dissolved, then it would be super saturated. Okay, that's what these terms mean. Yeah? Okay. Soluble and miscible mean the same thing. Ellen, again, what does it mean to be soluble? So if we say, what does it mean to be miscible? If something is not soluble, we say insoluble or immiscible. So this is a little bit of an old-fashioned kind of term, but we could still see it. Okay. Next page, and I turn it over to you. Solubility versus temperature. These look different than the previous page. Yeah. Go ahead, Joey. What did you say, sorry? So they're not going to just, why? You know, 1,000,000%. When you imagine a gas, what do you imagine? Pause. What is temperature directly related to? With everything, but a lot, we use the relationship a lot with gases. Temperature is directly related to the kinetic energy, the energy of motion. Gases, super crazy freakazoid chaos. So are they going to be very cooperative? No, they want to be expanding, demonstrating those high energies. So if we give them more energy, they're just going to use that to escape. In soda bottling companies, they bottle before they can put the lid on their bottles, seal their cans, to keep the carbon dioxide. Their workers have to wear winter coats or some kind of insulation because they keep it at a low temperature to try to get as much carbon dioxide to remain before they can put the lid on. So to keep your soda more carbonated, we should keep it, in the refrigerator versus out on the picnic table in the sun, if possible. Okay, so can we take 5 minutes and then we'll take a brain break? Can you answer this question? Oh, giving you the answer. So, can you answer this and this? Okay, so can you come up with an answer for both of those? First, engage on your own, check in with each other, or do it together. And let's see, 4 minutes. So water has a choice. Yeah, water has a choice. Hang out with xenon, hang out with nitrogen. and you are being told xenon is more soluble. Okay, so not, well, I am going to refer back to that meme. So the dude's trying to decide, why is he choosing xenon? You tell me. Why? You are absolutely correct. Why? Because there's more electrons. So, why? What are we missing? What are we missing? What controls the strength of London dispersion? The number of the electrons. Why? What does having more electrons lead to? Go. So, yeah. Very good. Do we understand what that means? That electron cloud is moving. The more electrons, the more a little bit of negative that is. The greater that little bit of negative, the more polar it's tending to be. So that just is more attractive directly. So xenon having a higher number of electrons, it's more polarizable. Well, so versus nitrogen, they're both nonpolar. They're only going to have London dispersion. So therefore, there's the particle attraction of xenon and water is greater than nitrogen and water. But what specifically is the particle attraction? What do we call it? And I didn't go over it before. So if you have two molecules that can hydrogen bond, they're going to hydrogen bond with each other. If there are two polar, but they can't hydrogen bond, they're going to create dipole-dipole together. But here we have water that can do all these, but xenon, just on dispersion. Can water hydrogen bond with that? Go, Jacob. Ooh, say it one more time. Ooh, is it ion induced dipole? But close, so close. We say that water is polar. Being polar means it has two areas of charge. It has a dipole. So water, being polar, will create attraction with xenon. We're going to say, what is the strongest kind of? It can hydrogen bond because there isn't any hydrogen sandwich it can make. So this is one-sided, partially negative, one-sided, partially positive. Those are always there. Well, this is going to alternate. So what this is going to do is it's going to force xenon to show a positive on this side. So it's going to influence it to be almost like it's polar. Yeah, dipole-induced dipole. So the dipole-induced dipole would be stronger with xenon than with nitrogen. All right. How about this as a super duper prize? It would be a baby Yoda, also known as cool. Say again. But it has baby Yoda. Very good. Very good. Very good. All right. Remember, sorry that I'm still going on.